Hi Josh. Okay, so for activity number 3 in Unit 6, I'm going to address the issues that you asked about. Okay, so whenever you're adding vectors from a picture or something like this to come up with a single vector, a lot of times you're going to have to change some things around. So the first thing that I'm going to do is, instead of writing AB minus BC, I'm going to change it so that it's an addition. So AB plus CB instead. Okay. And when I look at these vectors, I have A, B is in this direction, and then CB is in this direction. So right now, that doesn't really help us all that much because we got head to head or tip to tip. So what I can do is I can take vector AB and I can shift it down here. So now I still have vector AB. It's the exact same vector as it was up here, but it's in a different location so that I have my tip to tail. And then when I connect these two vectors, this is what I end up with. So there's two possible answers for this here. It can be FA or it can be DC. So hopefully that makes sense. All right, so the last example that we have down here, we have EA minus FB plus EC. So EA is right here. So I'm actually going to change that around again. So plus, oops, that should be an F. So EA plus BF plus EC. Okay, so now right away when I kind of look at this here, if I'm looking at EA plus EC, so EA goes from here to here. EC is right here. I'm actually going to erase those other vectors that I have over here so that they don't confuse us too much. So I have these two vectors when I'm looking at that. So EA plus EC. And then if I throw BF into the mix, I'm going to use a different color for that. So BF is going in this direction. I can see right away that EC and FB, they cancel each other out. They're going in opposite directions. So the answer to this one right here is going to be simply EA, because BF and EC, they go in the opposite direction, so they cancel each other out. So hopefully that makes a little bit of sense for you when you're working this question. The whole point of these questions is for you to recognize that you can move vectors around but still maintain the exact same thing. All right, so let's go on to the next one that you asked about. So this is 2B when we're looking at coming up with the bearing notation. I believe you said you found the magnitude, which is 30.9 newtons. When you're finding the bearing, there's a couple of ways that you can do it. I'm going to do this one here by making the parallelogram, and then when I work through example C, I'm going to use components. All right, so the first thing that I'm going to do right here is I'm going to basically take this vector right here. I'm going to shift it so that I have my tip to tail. And now from here, I'm going to draw my resultant. So this will be my resultant. Okay. I'm actually going to change the color so that we know what it is. So this is my resultant. And I'm going to need to put an arrowhead on there. All right. So from here, after figuring out all these angles, so this is 10 degrees down here. This whole thing is 65 degrees. So that means this little piece must be 80. Okay. So because this is a parallelogram, the full angle down here is 145 degrees, which means this here has to be 30 because co-interior angles have to add up to give you 180. So that's how we can come up with this value. We know that this is 12 newtons. And then using cosine law, we can find that the resultant is 30.9. From here, we are going to find this angle. So the one that I'm going to shade blue. So this blue shaded angle is going to be theta. And we're going to use sine law for that because it's not a right triangle. So I have sine of theta over 12. It's going to equal sine of 35 over 30.9. So then from there, I am going to have theta equals the sine inverse of 12 sine of 35 over 30.9. So when I work that out, we are going to get a value of 12.9 degrees. So this right here is 12.9 degrees. So the bearing notation, the bearing always comes from the north. So we need to know what the value of this full angle is. Not that full angle, sorry, not the green one. I'm going to just get rid of that. We need to know this angle right here when we're describing the bearing. So if I go from here all the way to this side, it's 65 degrees. From here to here, it's 12.9. So I need to know what that angle is going to be. I'm just going to use a different letter. So it's going to be 65 minus 12.9, which is going to be so 65 minus 12.9, 49.1 degrees. So therefore, the bearing is about 0.49. So hopefully that makes sense. It's all about figuring out what the angle is going to be relative to the north going in a clockwise direction. All right, now this question right here, I'm going to do it using components. So for vector A, it's saying that it's in a quadrant south 30 degrees west. So if I'm south 30 degrees west, it's going to be roughly right here. Okay, and it has a magnitude of 20. Okay, and then my second vector that I'm working with is going to be, so this is going to be vector B. So that's north 67 degrees west. So right here. So I know this is 67 degrees. It has a magnitude of 35. All right, so now I'm going to put in some other information. If this is 67 degrees, this one right here must be 23, which is going to be really important because I'm going to turn it into a right triangle. The vector A, same thing right here. This is going to be 60 degrees if it's 30 degrees south. Okay, so then now I'm going to break it up into components. So for vector A, I'm going to have an x component and a y component. Oops, let's pretend that's straight. All right, so the x component is right here. I know that cosine is going to give me the adjacent, and I know that it's going to be negative right there, so I'm going to have negative 20 cosine of 60 degrees. The y component is going to be down here, and the y component is going to be sine, and that's going to be negative 20 sine of 60 degrees. When I do vector B, same process. When I look at x, so the angle that we're going to be working with is going to be 23 degrees. And again, that value is going to be negative. So negative 23 cosine of 23 degrees. So that's the x. Now in this case, the y is positive because we're above the axes. And if you want to think about it, sine is positive in that quadrant. So we're going to have, whoops, that value shouldn't be there as 23. This number right here is actually 35. So minus 35. This will be 35 sine of 23 degrees. So now I need to find my total. So when I add that together, so I get negative 20 cosine of 60, 35 cosine of 23. So this value is going to be negative 42.2. When we do the y component, we're going to get, let me do that over, so negative 20 sine 60 plus 35 sine 23. So this value right here is going to be negative 3.6. Okay. So when we are going to figure this out, so the resultant value that we're going to get, so the resultant, when I draw that, it's telling me the x component is negative 42.2. So this is going to be the x. The y component is negative 3.6. Okay, so that's going to sort of help us determine where we're located. So if I add the y component right here, our resultant is going to be down here, and the angle that we're going to end up finding is right here. So this is negative 3.6. This is negative 42.2. The resultant, we'll use the Pythagorean theorem. So we get negative 42.2 squared plus negative 3.6 squared. Which is going to give us 42.4 roughly kilometers per hour. Now when I want to find the angle, it's a right triangle, so I'm going to use tan, so tan of theta of negative 3.6 over negative 42.2. So theta equals tan negative 1 of those values of 0.0853. So theta is going to equal approximately 4.9 degrees. That means this angle right here is the 4.9. So that means this angle down here is going to be 85.9. So when I make my final statement, it's 42.4 kilometers per hour, and it's going to be south 85.1 degrees west, or you could say west 4.9 degrees south. Either would work. So this is how you would do it using components. Component form is actually probably a little bit easier sometimes because you just have to put it into the right quadrant. You're always going to be creating sine and cosine relationships in order to figure it out. So that's just my personal preference is this way. However, the parallelogram law using cosine and sine will also work. All right, so the last example that you asked about is this one right here. I'm not going to work it through for you. In this case, I think you said that you believe that it's sometimes true, and that is correct. I'm going to say to you, you need to think about the size of the angle. So if you were to maybe work through an example that had, so let's say U plus V or 30 degrees versus at 150 degrees. See what's different in terms of the magnitude. You can probably tell by looking at it right away, even though my pictures are not to scale, but this question is all about considering the size of the angle. So hopefully this helps. If not, let me know and I can hopefully clarify again.